So we have seen something known as feed-forward neural networks, right? So we have an input layer, hidden layer, and an output layer. So input layer takes your input as X, right? So all the input, whenever we talk about input, mostly denoted by X, right? And whenever we talk about the predicted output, it's denoted by Y hat. The true output is denoted by Y, right? So it is going to produce something known as Y hat, right? And then we have something known as hidden layers, right? So generally, if we randomly Google what is a feed forward neural network, we will be able to see something like this, right? Everyone is going to use something on the hidden layer, something on the input layer, which is X, then something on the output layer, which is Y hat, and then some weights and biases, right? So in the deep neural network series, we have seen that everything that flows between input to the hidden layer is the weights sitting between input and hidden layer. Weights always and always sit on the edges. Similarly, between hidden layer to output layer, let's call it WHO, right? WHO is a matrix which denotes that we have some weights sitting on the edges between hidden layer and output layer. A fully connected neural network is always going to have dense edges, right? From one node to every other node in the next layer. From one node to every other node in the next layer, right? Yeah. Now, when we talked about recurrent neural networks, we saw something like this, right? Where we had a recurrent unit, right? So we have XT, we have hidden state, and then we have this particular cell that denotes a recurrent cell, and then YT or Y hat T, right? So T is denoted as time, right? So the output Y hat at time T is a function of input xt and the past hidden state or the past memory, right? So what the goal of this video is not to understand recurrent neural networks. The goal of this video is to help you revisit where we started with deep neural networks, and we are trying to solve recurrences, we are trying to solve sequences. Now we came on to recurrent neural networks and the problem with recurrent neural networks, so that we can introduce something known as transformers, right? So this is the piece of code that I trained, that I trained an RNN on, and this is nothing but we're trying to predict the stock price of Apple for the last 200 days, right? So this is the training history, and this is the right side is known as the prediction behavior. So blue is the actual line, and orange is the predicted line, right? So let us observe this thing. So we can see that there is a very slight lag in the predicted curve versus the actual curve, right? So this is a typical behavior of RNN, right? The other thing that we can see that the curves, or basically the spikes, are a little smoother in case of RNN's predicted behavior, right? Now, one more thing I want you to observe here is, let's observe what is the sequence length here is 3, right? So what that means is I am trying to tell my recurrent neural network that find the probability of the stock price of Apple on T4 given T3, T2, T1, right? So that's why we call that the input sequence length is 3, right? So let me give you one more example. Yeah. So this is what we are trying to do, right? So here, just imagine that what I'm trying to do is I'm just trying to tell it that give me something like this. So given the prices of Apple stock for, you know, T Tth day, T plus 1th day, T plus 2th day, help me predict T plus 3th day, right? So we have small and short sequence window in this case, right? So in case of smaller sequence windows or smaller sequence length, RNNs, work nicely. But what happens when these sequence length grows, right? Because it's not always the case that the stock price of Apple on the fourth day is always going to be dependent on the past 3 days, right? So tomorrow's stock price might also need global context, right? It might need past 100 days of stock data. What do we do in that case? The other thing I want you to think about is, what about sequences? We are treating everything in a sequential manner, right? We are moving from left to right in a unidirectional way, and we are treating everything as sequence, right? How do we parallelize that computation? Right? Because if we try to unravel the dependency graph, let's focus here. If we try to unravel the dependency graph, it's going to show us that Yeah, it's going to show us that x2 is dependent on, I mean, this particular, let's say y2, y hat 2 is dependent on this component and this is dependent on this component, right? So we have a tight sequential dependency, right? So how do we parallelize it? The other thing that I want you to focus on is smaller sequence length. The problem, when the problem is small and local, it works fine. What if the sequence length grows, right? When the sequence length grows, it suffers with something known as weak gradient flow, right? Now what do I mean by weak gradient flow? I simply mean that back propagation through time, when which happens in case of RNN. So we know that every neural network, let's revisit it, every neural network goes through a forward pass, computes loss, and backward pass, right? So when RNN goes through a forward pass, it's going to go nicely, we have no issues. But when it goes through backward pass, when the numbers are going to get multiplied, right? And let's say if the sequence length is 100, in the chain rule, when I'm going to multiply the numbers, and let's say if the values are getting smaller than 1, 0. 0.9, 0.8, 0.08, when you multiply them cascadedly in a sequence 100 times, layer after layer, it's going to, approach and tend to 0. That is what we might call as a weak gradient flow or vanishing gradient problem. The opposite is also true, that it might explode, which we might call as exploding gradient problem, right? So gradient problems, training stability is one of the issue in case of RNN, right? Forgetting things is also one of the issues in RNN. So basically this is how RNNs behave. Let's try to simulate a simple thing. Yeah. So now what we're trying to do is we are just trying to predict stock price given the past 10 days of data. So given 10, it's going to predict 11. So here the RNN that we are trying to simulate is more or less perfect, right? There is no lag, right? It is helping us trace very nicely, which is, not always the case. Now, for how does it, we have seen that with time series stock, it behaves like this. With text, if I do the quick brown fox and let's say I do generate text, it should ideally generate the next token and the next token, right? So it might generate gibberish based on my training. So it might be good, it might be bad, but we can see that it's going to generate tokens, right? Or although it's generating gibberish, right? Now let's do weather forecasting. Let's try to simulate what's going to happen in this case. So here, what we're trying to do is we are trying to forecast the weather for the next day given the past T sequences, right? So this is what the behavior of RNN is. Now the problem with RNNs, as we discussed, since everything is sequential, there is no parallelization, right? Each word is processed after the previous one, right? Because there is cascaded dependency. So there is very tightly coupled dependencies. We cannot process the word 10 until we have processed words 1 to 9, right? That's why we cannot, it's very difficult to parallelize it, right? Although we might have progressed with all the acceleration in hardware, we might have the best of the best GPUs, but if the algorithm does not allow us to parallelize it, how the hell would be, right? So that's why this is one of the biggest disadvantage, that we have sequential processing in case of RNNs. So this makes the training extremely slow because GPUs cannot process multiple words simultaneously, right? Then long range dependencies are very hard to model. We saw this with input sequence window. In the Apple stock example, we had an input sequence window of only 3, so it worked fine. But what if I want to make it 100, right? So it's very hard for me to model long range dependencies, like token 1 and token 100 might want to interact with each other. If I make them interact with each other, then I will suffer with something known as exploding gradient or vanishing gradient problem, right? So during the training time, with, let's say, when the sequence window grows, gradients must back propagate through every time step, we know that. And over these long sequences, the gradients either vanish, that is, they tend to go to 0, they become very small, or they explode, right? Let me show you something. Yeah, let me show you a visualization of vanishing gradient problem. Yeah, you can see when the layer gets dense and we stack layer after layer, this is what happens. Till the time you reach the inputs, I mean till the time you reach the earlier layers, we have already forgotten what we learned, right? Yeah. Okay, so I think these are all the problems we have with RNNs and LSTMs. That is why we need a better solution, which we might call attention, right? So that is why we want to introduce a new architecture, a new way of thinking. So we want to ideally design a model that obviously captures all of these sequential relationships, but what if it tries to capture without the recurrence model, without the recurrence relation, and without the convolution. So we've seen convolutional neural networks, we've seen recurrent neural networks. What if we can do something different which solves all of these problems more or less, right? Okay, see you in the next video.